Welcome to a lesson with Dr. Powell. Let's discuss why asymptotic inequalities for polynomials are valuable when we're looking at series and integrals and doing comparisons. Now, because we can compare a series to an integral and whether or not the series form converges or diverges is the same as whether or not the integral converges or diverges, as long as we make a couple assumptions on what's going into here. The following procedure will work both for integrals and for series. So suppose, for instance, that we have something like, and let's do an integral, but this also can be thought of in terms of a series. All right, and let's suppose that we have something like x squared minus x plus 1 all over, and let's do something like 2x cubed, so 2x cubed plus x, okay, and maybe minus 1 or something. All right, now we have a question. Does this converge or diverge? And we don't even have to integrate to answer this question, whether or not this converges or diverges. And the idea is by comparison. I mean, straight away, we can kind of look at this. If we ignored everything else and just look at the leading terms, we kind of see, and native cancellation, we kind of see like a 1 over x type of thing times a half. Now, the integral of 1 over x actually will diverge. It's the one right in between, and we get divergence on both sides. So when p is equal to 1 for the p series test, we end up getting, so for x to the negative p, if we're looking at this, or n to the negative p, both of these, when p is equal to 1, we get divergence. It's called the harmonic series when p is 1. Okay, so based upon that idea, we get a target. So if we're going to show that something converges or diverges, we first get a target. We get something we want to prove or show. So it seems reasonable to prove that this might diverge just by a little rule of thumb, intuition. So let's see if we can go about that. So in order to show that, it'd be nice to show that this integrand right here, this is eventually asymptotically, so as x goes off to infinity, is eventually greater than or equal to some multiple of 1 over x. So if we can show that, then we'd show it diverged, because this will be bigger than something that we know diverges, so hence we'll make this one diverge. So if something's bigger than something that diverges, then of course it diverges. That's kind of the idea that we use. Now, this constant could be a small fraction, a big number, whatever. We just need to show that this is true, because if 1 over x diverges, then any multiple of it would also, if we put it into an integral form, an integral. So let's see how this would work here, how we'd get this constant. So we use the ideas that we have for polynomial inequalities by on the top and the bottom. If we want to show this is bigger than or equal to something, on the numerator we show greater than or equal to, but the denominator we show less than or equal to. Because if we want something smaller, that means a bigger denominator. So what's something bigger than this in terms of the leading term? You'll notice that this is positive right here, and eventually this is like that, so we just basically double the leading term. So we could even say 4x cubed. That was one of the principles we had on finding something that was bigger in a polynomial. Now here we need a polynomial that's less than. So makes sense, since what we're subtracting off can not be more than half of what this is eventually. We just simply say 1/2 x squared. So using our technique, we now have a polynomial, or we have a fraction of polynomials, which looks simpler, which is less than this one, eventually for large enough x. This is an asymptotic inequality. So rearranging this looks like, and canceling out a couple of things, this looks like 1/8 times 1 over x. We have 1 over x. Okay. All right, so we have found our constant, and we have established our inequality. Therefore, so we know since this diverges, then this must as well. So we know we have just proven that this integral diverges. Well, we've actually also proven that the following series diverges as well. Same technique, no difference. So both of those guys diverge. Thanks for watching.